Hi, let's talk about a special instance of least squares that winds up being rather important. So consider the instance where x transpose x is equal to I, and x is full rank. And even maybe what appears to be a little bit stranger, let's consider the case where x is n by n. So now this may seem to be an odd thing to do. Recall, if here is our, if our y is three-dimensional, y1, y2, y3, and our y is some point in three-dimensional space, and our x is three-dimensional, then y hat will just be exactly equal to y, because the dimension of the space we're trying to project on is three-dimensional, our original data is three-dimensional, so this extends up to n dimensions. So it seems like if we have a full rank n by n matrix x, what's the point of doing least squares at all? So we'll get to that in a minute. But notice here, if I want to solve my least squares equation, y minus x beta, and minimize that with respect to beta, then my estimate is, of course, we've discussed this, x transpose x inverse x transpose y. But in this case, x transpose x is just I, and so it works out to just be x transpose y. So, and looking at this, if my x is equal to n columns, then this means that it's the inner product of x1, the first column of x with y, is the first coefficient, the inner product of x2 with y, and so on, all the way up to xn with y. And my fitted values, my y hat, which is now going to be x transpose y, well, this works out to be nothing other than the summation I equals 1 to n xi times the inner product of xi with y. Now, what's interesting is imagine the case where instead of having x, I have just a few columns of x. Let's say x subset. I'll just put a little x sub s. Well, x sub s transpose x sub s, let's suppose it only contains p, a random collection, not a random, but any subset of the columns of x. Well, it also has inner product I because, again, just because of this statement up here. Well, then this whole argument just goes through, and then it says that my y hat fitting the subset of x rather than the full basis x, just fitting the subset of x, right? That y hat is just the sum over the collection of i's in the collection of indices, the subset indices, xi times the inner product of xi and yi. So what this means is, if I have my full design matrix and it's a full rank basis for Rn, my coefficients just work, and it's an orthonormal basis, my coefficients work out to just be the inner products between the basis elements and my outcome. And if I want to fit, instead of a n-dimensional version of this basis, if I just want a p-dimensional version of this basis, I can just grab the relevant subset of these coefficients, right?